Worked example 8.2b is very similar to the last question. In fact, they're using the same equipment as in the last question. Sorry. I'm just going to change my grip. Okay. Magnetic field, again, is 4 milliteslas, and the area of our loop is 1.5. The thing that changes in this question is the angle. So it starts off flat and then the loop twists up. The important thing to see here is this is our angle here. So that would have been the right angle. So we're measuring between the right angle and the current field line, where the field line is now. So we need to draw that in. So that would have been the right angle, and this angle in here is 20 degrees. Right, so, and this takes place in 0.1 seconds. So that's going to be delta t equals 0.1 seconds. The area is unchanged, still 1.5 meters squared. So just check everything. Magnetic field, it didn't change. It stayed at 4. So B equals 4 milliteslas. It stays at 4. The loop twists up. That's what's changed this time. Determine the EMF generated. So determine the EMF generated. So we could go with, what have we got? We've got B equals 4 milliteslas. That's 4 by 10 to the negative 3 teslas. We have the area is 1.5 meters squared. Let's change my grip. We have delta T, 0.1 seconds. And this time we have an initial angle, which, remember, we're measuring the angle to this line, and it would have been at 90 degrees to start with, so it was straight along that line, so the angle is 0, and then it rotates through 20 degrees. Right, so EMF is what we're after. Negative N change in BA cos theta divided by change in time. And this time it's the theta that's going to change. So it'll be negative N BA change in cos theta. Change in time, negative N BA cos theta F minus cos theta I divided by change in time. Righto, so N I didn't write down at the start. There's just one loop, so N equals 1, negative 1, times the magnetic field strength, 4 by 10 to the negative 3, times the area, 1.5, and then we'll have cos 20 minus cos 0 divided by the time change, which was 0.1. Put that all in your calculator and you end up with 3.6. It will be negative MV. Now, the book is doing a thing where it doesn't really want to worry about this, if it's just asking for the magnitude and not the direction or whatever, and they're going absolute value, which is indicated by those two lines, and just going 3.6 millivolts. So that would have been 3.6 by 10 to the negative 3. When we use the absolute value, we can just drop the negative off. The next question, the next example, is the same again, only this time they're changing the area. So if you look at it in your textbook, I won't work it out because it's straightforward now that you know how to do it. The area of the loop has changed. It's gotten smaller. So it went from 1.5 down to 0.6. So you'll see here. Oh, I thought I switched it off, but I accidentally, no, it's still going, I think. Oh, I see. Area final minus area initial. And again, they've used the absolute value so they don't have to worry about the negative sign, 36 volts. So that's pretty straightforward.